All right, welcome everyone. Nice to, see you over the web again. I guess to start out today, I just want to make sure that the sound is okay for everybody before we continue on with the lecture. All right, thanks for the feedback, Akron. So today I'd like to finish up some discussions on gels from the lecture on Tuesday, and also talk a little bit about self-assembled structures, particularly self-assembled structures in this area at the interface of gels and soft materials. So looking at just a few examples of self-assembled structures that fall into the same sort of broad material category and that are of interest in sort of the same type of considerations. So to review from last time, we discussed about how hydrogels were an extremely interesting class of material for a wide variety of different technological applications: biomedical, some in electronics, high technology things like actuators, and then everyday items such as food and orthotic insoles. There are a wide variety of different structures that can make gels, and by controlling the structure of the material, we saw that gels could do some fantastic things. So last time we discussed about ideal polymer networks, such as the tetrafunctional PEG developed by Shibayama's group. We talked about how preparing polymer networks with multiple different polymer chemistries in very particular ways, such as the double network materials developed by Jianping Gong, lead to very, very tough and strong hydrogel materials. So things with moduli and toughness that are significantly greater than the gels we're used to thinking about in our everyday life that are relatively fragile. And we talked about a couple different examples of responsive block-copolymer gels, where we could essentially use changes in thermodynamics in order to tune the association or dissociation of different crosslinks or physical associations within a network, and in this way change its structure and consequently the properties of the hydrogel material. So today I'd like to continue discussing a few different types of gels that illustrate the different way that SANS can make structural measurements and provide structural information about hydrogels, and the types of models that people use for modeling these different types of gel structures, and then also illustrate some of the interesting capabilities of these type of hydrogels for technology and why these are interesting structural problems to think about. So I know Professor Waits talked a little bit about colloidal gels during his lectures, and so this should be hopefully a topic that's somewhat familiar to many of you. And I'd like to start there with an interesting example that was performed by one of my colleagues here at MIT of this colloidal gel system. And I select this example because this particular recent paper from Nature Materials includes a relatively detailed neutron scattering analysis that allows us to understand what type of structural information we can extract from these materials. So the particular colloidal gel I want to talk about is they refer to as an organohydrogel, and it's basically a nanoemulsion prepared from silicon oil in water. So what the investigators do, Matt Helgeson, who's now at UCSB, I think in the Department of Chemical Engineering, is the lead author on this. It's out of Pat Doyle's group here in Department of Chemical Engineering. What they did was they took silicon oil in water emulsion, and they processed it in such a way that they reduced the average droplet size of the silicon oil droplets to be in the range of order 100 nanometers, so relatively small silicon oil droplets in an emulsion, and this is what they term a nanoemulsion. And then by tuning the interaction between those droplets using small polymers in the solution, they're able to induce gelation in a thermoresponsive manner within the materials. And so thus the term an organohydrogel, because it has an organic oil, the silicon oil, dispersed in water, making it a hydrogel. And essentially the colloidal particles, these organic silicon oil particles, serve as the colloidal object that forms a colloidal gel in this type of system. And so there's a small picture, let me grab the pointer here, a small picture showing these materials. So at 23 degrees C in the low temperature phase, and this is basically an inversion test for looking at gelation. An inversion test is not really a rigorous mechanical test, but you basically take a vial or cup of your material, turn it upside down. If it flows out, it's not a gel, and if it doesn't flow, it is a gel. So it's a very fast and sort of crude tests for solid-like behavior. So they show one of these inversion tests here, and then accompany it, what I've shown on the right-hand side, with some very detailed rheological characterization. If you just look at the image at 23C, you see the material flows. At 50 degrees C, you see it doesn't flow, and it shows solid-like behavior. They plot in this graph on the left-hand side the G prime, the elastic modulus, and G double prime, the viscous modulus, both as a function of temperature in the gel. And so you see you increase to a temperature right around 35 degrees C, and both these increase very rapidly. The elastic modulus, which is the dark curve, becomes higher than the viscous modulus by about an order of magnitude at the highest temperatures, which is indicative of the solid-like behavior characteristic of gelation. On the right-hand side, you see more detailed frequency-dependent rheological analysis. So at low temperatures, you see the characteristic terminal behavior for the materials with the scaling of G prime, G double prime linearly with frequency. As you heat it up, you see the scaling change to G prime and G double prime, both go as frequency of the 1/2, and then finally at the highest temperature, you see this frequency-independent modulus over a range of frequencies that's indicative of the formation of a gel. Now, in these types of organohydrogels, the associations between the colloidal particles are purely physical. So if you lower the frequency enough, there should be some sort of characteristic relaxation time given by the characteristic dissociation time of the particle interactions. However, in the frequency range that the authors were exploring here, this relaxation is slower than that frequency range, and so therefore it can't be observed in the mechanical property data. So I'm going to skip ahead 2 slides quick just to show sort of what the cartoon concept of the structures is before we talk about the detail of the neutron scattering fitting. So the cartoon concept of the structure is that we have a relatively polydispersed mix of oil droplets, and these are illustrated by the white spheres, and each of these oil droplets is covered in a surfactant to help disperse it in the water phase. And then in order to modulate the interaction between the oil droplets, the authors add short polyethylene glycol polymers to these materials. At low temperature, as they show in this upper left inset, the polyethylene glycol polymers don't strongly associate with the colloidal spheres, and so you get spheres that are relatively free to move about in solution, and you don't form a gel because you don't have a strong attractive interaction bringing the spheres close together. So essentially you have a colloidal suspension under these low temperature cases. As you raise the temperature of the material, the end groups on the polyethylene glycol, which are somewhat hydrophobic, will tend to insert into this surfactant layer on the outside of the oil droplet, and therefore become anchored in the edges of the droplets. Because each polymer chain has 2 ends, it can anchor into 2 separate droplets, and this provides a short-range attraction, basically due to this physical cross-linking between droplets. So you essentially introduce an effective attractive interaction due to the bridging of these chains, and that effective attractive interaction leads to a coalescence of the droplet, or not a coalescence, excuse me, but a sort of aggregation of the droplets into a network structure, which is illustrated down here on the bottom side of the picture. And so the goal of the authors using SANS is to try to capture the different length scales inherent in this structure. The length scale of the individual droplet and what its structure looks like, and then this longer length scale structure involving these sort of correlation lengths based on the formation of holes within the sample. So in order to do this, they develop a SANS model, similar to one of the models that we looked at last time, a Perkus-Yevek model for capturing gel structure. So the overall scattering pattern can be characterized as containing 2 contributions. The scattering from the emulsion, which they denote IQ of the emulsion, and scattering from the PEG diacrylate. This is that polymer that they use to bridge between the different particles. And so, depending on contrast matching, you can eliminate or not eliminate either one of these scattering effects. And so, a lot of the development of scattering functions focuses on looking at the scattering from the emulsion. So, the scattering from the emulsion they model using a Perkus-Yevek model of the gel structure. And last time we looked at Perkus-Yevek hard sphere model, in this case, the authors use a Perkusiewicz model with a square well potential instead of a hard sphere potential for their spheres. So the structure factor is captured, S of Q is given as C of Q over 1 minus rho times C of Q, where C of Q is the direct Fourier transform of the correlation function. And this information has to be obtained by applying a closure approximation, in this case applying it using the square well potential instead of applying it using the hard sphere potential as in the previous result that we showed. So the square well potential that the authors apply in order to derive their form of S of Q is shown here. So essentially infinite hard sphere interaction for r less than the average d, or diameter of the particle. Then out to some characteristic length lambda, they apply an attractive interaction, epsilon over kBt, and then say that the particles are non-interacting at an interaction length beyond that. So a relatively standard square well potential. They again treat the form factor, P of Q, as being the form factor for a sphere. So J sub 1 is the Bessel function. They have to capture polydispersity in the spheres, also in this organohydrogel model structure, as we did in the block copolymer gel structure. And so this is captured, again, by the same sort of integral to get an average P of Q. And here the polydispersity function that they use, F of D, I've shown at the bottom of this slide. So they use a combination of small angle neutron scattering and ultra small angle neutron scattering in order to capture a very wide range of length scales in the material and be able to fit the structure of these gels. So what they show here is a data set in red in the graph on the left and a data set in blue. The data set in blue is acquired at low temperature where the particles aren't in their aggregated state. And so what you see is scattering essentially due to the packing of the spheres, which is what's fit with the dark line. And then a Guinier regime, or basically Q-independent regime, which comes out at very low Q, indicative of the fact that essentially what you have is a colloidal suspension or colloidal solution of particles. And there's some interaction between the particles, but there aren't these larger length scale inhomogeneities. Essentially, the particles are all isolated individual objects. In contrast, when they raise the temperature, you see the scattering traces shown in red. And so you see the appearance of a characteristic structures with a correlation length of 480 plus or minus 50 nanometers that can be fit at the very large length scale. And then you see these same higher Q or sphere packing type of structures with some minor changes in the sphere packing, but mainly the appearance of this large correlation length at higher length scales, which is indicative of the formation of this gel network in these types of materials. Using the SANS measurements actually allows measurements of very careful measurements and extraction of the interaction parameter. So not only can the authors understand the structure of the gel, but they can also understand its the interactions between the different particles. And so here are some intensities plotted as a function of Q. And by fitting the structure factor of the droplets with this square well Perkusiewicz model, they can then extract the square well energy that gives the best fit. And so the figure on the right is essentially a zoom in of this upper corner of the figure on the left. And so you see the curves magnified. And then the inset to this figure is the best fit value of epsilon over kBt for what the effective attractive square well potential is between the particles. And what you see makes sense in light of the structural changes that are observed in the gel. At relatively low temperature, the attractive square well is relatively shallow. It only has a depth of something like 0.3 to 0.4 kBt. So the well depth is less than the thermal energy. And as you heat the particles up, they see the well depth gradually increase, and you cross over the gel transition, which was about 35 degrees C. You go to well depths that are somewhat greater than 1, and at 60 degrees C, they see something approximately 1.5 value for epsilon kBt. And so a significant increase in the depth of this square well potential that provides the best fit to the data. So this suggests that indeed, upon heating, they're increasing the attractive interactions between the particles in this organohydrogel due to bridging by the different polymer chains within the material. Oh, sorry, too far. So one of the other things that the authors demonstrated, which was very interesting, is that they can actually make the structure permanent, remove its temperature responsiveness, essentially by photo-cross-linking it. So when they add a large amount of polyethylene glycol and incorporate acrylate groups under the end of the polyethylene glycol, now this polyethylene glycol diacrylate can be photopolymerized in order to form a polymer network within the organohydrogel structure. And so the authors prepare this in two different ways. The first one is by photo-cross-linking the material at elevated temperature and then cooling down. And what they show is when they heat it up to elevated temperature, they form the colloidal gel, and then photo-cross-linking of the PEG polymer freezes in the gel structure. It essentially removes the mobility because now the polymer chains that are causing the associations between the particles are not free to relax. And they've also polymerized in all the pores between particles, essentially filling those pores with networks so that the particles can no longer disassociate. And when they prepare the system in this way, essentially they can freeze in the structure in the gelled state and make it permanent. So now essentially there are two different gelation mechanisms in one molecule, or in one system, excuse me. One is the chemical gel formed by the polymerization of the PEG diacrylate, and one is the association of these different particles, of the silicon oil particles, which form the organohydrogel due to the thermal responsive association. Now in contrast, if the material is first photo-cross-linked at low temperature, not in the gel state, and then heated, what you see is only a much smaller increase in the low Q scattering relative to what you see if it's photo-cross-linked at high temperature. So comparing the figures on the left and the right, which are plotted on the same axis of the same absolute intensity scale, you see a relatively small increase in low Q scattering on the right-hand side compared to the larger increase in low Q scattering on the left-hand side. This is indicative of the inability to form this fully developed network with these well-formed large length scale correlation lengths due to basically aggregation of the different silica oil particles. And so schematically, you can think of this as relatively small aggregates of particles, but not interconnected in the same way into a macroscopic network, where now these particles are basically held apart by the polyethylene glycol network that was formed during photopolymerization. And so again, under whichever condition the material is photopolymerized, you're able to largely capture the structure using photopolymerization essentially as a method for immobilization. Alright, sorry, this slide appeared twice, so let me skip over it. Alright, so another very, very interesting category of materials that I'd like to discuss is the formation of fibrillar gels. And the example work I've chosen is from Darren Pochon and Joel Schneider's groups. However, this idea of fibrillar gels is actually really a very, very popular area in terms of development of different soft material structures. And essentially, this is really at the interface of self-assembly and gels, using the combination of small molecule self-assembly to form nanofibrillar structures, which then result in a gel when their large-scale morphology is prepared in a certain way. You also see folks like Sam Stoop at Northwestern University, Rafael Mazenga in Switzerland, Alberto Ciani and Eileen Miller in the UK, and many, many others working on this concept of peptide hydrogel self-assembly. And I think these are particularly interesting materials and have attracted so much interest for several reasons. One is that the peptide fibrils look a lot like structures in the extracellular matrix of native tissues. And so there's a lot of interest in being able to self-assemble fibrils from these biologically inspired components and then use this to make tissue engineering type of structures. So these gels are really particularly attractive for biomedical engineering applications. I think another interesting aspect is that because the peptides are relatively short, there's a good chance for researchers to be able to understand and apply rational design to the structuring of these systems, where it can be much more challenging in very, very complex protein systems. So this is one of the systems where people can get a very good handle on some of the rational design aspects, and there's been some very beautiful work understanding carefully the structure property relationships of these systems, where SANS plays a key role. So the peptide system one of the peptide systems that Pochon and Schneider worked on is essentially taking peptides that self-assemble into beta strand or beta hairpin type of structures. And so under certain conditions of temperature, ionic strength, or pH, these peptides become unfolded, and then by heating or by changing pH, they can induce the peptides to fold, heating in this case. When the peptides fold, they form these dimeric structures. And these dimeric structures form essentially to mask hydrophobic residues in the amino acid. Then these dimeric structures can assemble through hydrogen bonding between dimers into much, much larger fibers. So there are several length scales of self-assembly: the individual peptide folding, the peptide dimerizing, and then H bonding to self-assemble along a fiber axis to form an overall large length scale nanofiber structure, right? And so they show in this scale bar roughly the length of one of the folded peptides is of the order 4 nanometers, and as you'll see in some of the cryo-EM images, the length of the fibers can be much, much longer. This is very characteristic of these fibrillar structures. They're formed in general by relatively small molecules, and so they form fibers of narrow dimension, but the fibers will self-assemble rapidly in one dimension in order to form a highly extended aggregate in that dimension, even as they stay small in the other dimensions. So I think one of the sort of qualitative recipes for being able to self-assemble these type of fibrillar structures and fibrillar gels is finding things that self-assemble in a limited dimension in 1 or 2 dimensions, so that sort of self-limit their dimensionality, but that grow into very long structures in 1 dimension. Sort of a one-dimensional growth or crystallization process is one way to envision what's happening in these types of structures. So here I show the application of SANS and TEM in order to look at the size of these structures. And I apologize, there's a typo on this slide that I noticed after the slides were posted, that in the equation right here, there should be a Q square instead of just a Q. So I'll send in some new slides for reposting, but please make note of that. The show in piece A here, it shows a cryo-EM of these fibrils, basically showing their dimension, and from this the authors can measure the fibril width and produce a histogram shown here in figure B. SANS provides a really nice way to gain an ensemble average measurement of the fibril width, and essentially the plot of log Q times I should be versus Q squared will be linear in R sub C over 2, R sub C squared over 2, where R sub C essentially gives you a measure of the radius or the lateral size of the fibril. And so and you see that the fit to this is relatively good, so the line of best fit is shown here on the plot. And from the slope of this line of best fit, the authors can extract the diameter of the fibril in this structure. And what they find is that the fibril width measured by SANS agrees closely with the fibril width that they measure by electron microscopy, suggesting that providing strength to both. So Ming has a question. In this case, is RC the diameter of the fiber? In slide 10, great question, Ming. The answer is no, RC is not the diameter of the fiber. There's a little bit more detailed analysis that goes into the paper. RC is related to the diameter of the fiber by an order 1 constant. If my memory serves me correctly, their estimate for the diameter is its square root of 2 times RC is the quantitative estimate for the diameter. But I would refer you to the paper to check the exact development of the equation. But essentially, the scaling analysis I've presented, RC is related to the diameter by an order 1 constant, which I believe is root 2. All right, so in a subsequent analysis, the authors looked at the gels using SANS in a slightly different way. So when you imagine these sort of fibrillar network structures, similar to many of the other gels we've looked at, there are many different length scales of ordering within the material. And so one of the length scales of ordering is this local length scale of trying to measure the fiber diameter. The next length scale up is the length scale of looking at the individual pore size between the fibers. And then finally you have even larger length scales looking at large-scale correlations and homogeneity within the materials. And so in order to fit many of these larger length scale structures, Pochan's group uses a model where they have I of Q is equal to a term A over Q to the N. This is a porod-like scattering, which they use to fit the low Q behavior of the system, essentially capturing that hundreds of nanometers level length scale structure. And then they use a Lorentzian function, which has a characteristic exponent M and a characteristic parameter L. L is the correlation length in the system in their notation, so this is the same as C that we saw last time in many of the different models. And then M is this exponent in the Lorentzian function, and then a constant B to capture incoherent scattering from the background in the acquisition. And so the idea is that the Lorentzian function can capture high Q scattering in this system around 1 to 10 nanometers, whereas the porrod-like scattering is the low Q scattering structure at larger length scales of approximately hundreds of nanometers. All right, so I've shown here fits to gels at 4 different concentrations prepared from one of these model peptides. And so what you see is that the fits are quite good for this model to all 4 different concentrations from 0.5 weight percent all the way up to 2 weight percent. One of the things that's really fantastic about these peptide gels, really surprising, is compared to many of the other types of gels we've discussed, these peptide gels form gels at very, very low concentrations. So typically block copolymer gels, you'll see gelling in the range of 10% up to maybe 20% or even slightly more concentration of block copolymer in order to form a gel. So a relatively significant amount of polymer compared to fibrillar gels, which generally form in the 0.5 up to 2 weight percent, basically the range that's shown here in this manuscript. And so this is one of the really interesting aspects where understanding structure and gelation is extremely important in order to answer the question, why do these gels form at so much lower concentrations in the block copolymer gel? And in particular in the fibrillar gels, because we have these highly extended cylindrical fibers, you can imagine these cylindrical fibers essentially forming struts or beams in the gel that give it rigidity, even at a relatively dilute concentration of these reinforcing structures. And so you can get gelation at a relatively low concentration of the gelator. Right. So from these different fits, you can analyze and look at the trends in the fit parameters. And so there are 2. The first one is correlation length. And so the correlation length is this trace here, shown in the squares, and this is plotted on the right-hand axis of the plot. And so the correlation length decreases as the concentration increases in the gel. And this makes sense because of the increasing concentration, essentially decreasing the characteristic length of that pore and structure size as you add more and more of the peptide fibrils to the system. The second thing you see is that as the concentration increases, the high Q exponent increases from a value of about 2.59 up to a value of about 3.15, with increasing concentration from 0.5 up to 2. And this change in correlation length is essentially the value of this exponent reflects a mass fractal type of behavior in these systems, and the increasing exponent with increasing density is consistent with the mass fractal. It basically indicates that the mass fractal dimension is increasing, which is consistent with the increasing density of the system. And so again, this gives you some nice insight into how the structure evolves as a function of concentration within the hydrogel. Now these type of fibrillar hydrogels are extremely common from small peptides, but a discovery that I think is particularly fascinating and interesting for the development of technology is that these type of fibrillar structures can also be formed from whole proteins that are denatured. So this is one example from several authors who've done really nice work in this area. This is out of Eileen Miller and Alberto Ciani's groups at the University of Manchester. And what they did was took lysozyme, a widely available globular protein, and denatured it. In this case, using the agent DTT to assist in the denaturation, along with heating up to high temperature. When you denature the protein, it causes it to unfold, and so it puts its hydrophobic core, it potentially exposes its hydrophobic core, and also has now a lot of groups that can participate in hydrogen bonding and salt bridging available for interaction. What was found by Ciani and Miller is that when you allow this protein to refold, it doesn't refold into its original shape, which is actually common for proteins. Few of them will spontaneously refold into their original fold, but instead it forms these beta strand-rich fibrillar structures, similar to the oligopeptide fibrillar gels. And this ability to form fibrillar gels from denaturation of globular proteins has been observed by a number of different authors, and in fact, this is one of the interesting pieces of science being investigated in trying to understand the onset of certain neurodegenerative diseases, such as Alzheimer's disease. So I think this is a really fascinating piece of science that we're learning so much about fibrillar gels and applying neutron scattering in particular. And there's some here from this study shown on the left to understand the structure of these gels. And what's very fascinating and interesting is how general this mechanism of gelation might be. There seem to be a growing number of proteins that are demonstrated to fold into these type of fibrillar structures when they're induced to misfold. And so this induced misfolding can potentially provide an interesting new mechanism for material preparation and understanding of relevant biomedical challenges. All right, so at this point, let me pause and see if there are any questions. All right, well, let's continue then. So I had mentioned that these sorts of fibrillar structures can be formed by a wide variety of different molecules that might have some sort of directionality to their self-assembly. Right, this idea that a molecule would want to self-assemble or stack in one dimension, preferentially two other dimensions. And so I just want to show one example of this that's very much different than the peptide examples, and that I think illustrates the sort of broad utility of self-assembly of these nanofiber structures to produce different type of interesting materials. And so this specific example is from the group of Bert Meyer in Eindhoven. And this is a discotic type of molecule that self-assembles into fibrillar stacks. So one example of the molecule is shown here in the upper left. And they schematically illustrate this molecule as a central core with three arms coming off the molecule. What you see in the chemical structure is that the central core of the molecule is a planar benzene ring, and around this are different hydrogen bonding groups, essentially amide groups, which are potentially linked to more hydrogen bonding groups and more planar structures. And the amide bond itself also forms a highly planar bond structure. So essentially you have a planar center of the molecule, which is capable of pi-pi interactions up and down, and also has hydrogen bonding groups, which are capable of different interactions between groups. And so you build these structures that are highly interacting and highly stackable in terms of the center of the ring. And then around the outside of that, on each of the ends of these arms, you see there are 3 of these R groups, so a total of 9 of these R groups. And these R groups are composed of different types of branched or linear alkyl chains. And so this really gives a high solubility to the molecule around its edges. So you can think of this as a disc-shaped molecule with a propensity to aggregate in the center block, but a propensity to be soluble in the arms. Right? And so these arms can keep the molecule soluble in certain dimensions, while the disc center promotes aggregation in other dimensions, and essentially what you get is columnar stacks of the molecules, as illustrated schematically on the right-hand side of the page. And then depending on how the systems are prepared, they can potentially form different types of liquid crystalline order. And so I've shown here on the bottom an optical micrograph of columnar liquid crystalline ordering within these materials. So the Meyer group has produced a huge range of these materials that shows there's a very wide degree of chemical flexibility to their design scheme. And so they have discs that have amide chemistry, discs that have urea chemistry in terms of linking, and they can build up the size of the discs, which they call small, medium, and large, based on the size of the arm branches that they add. And so small discs just have this one benzene ring, and if they add other aromatic groups to the outside, then they can grow the size of the disc, and then by adding still larger aromatic groups and more aromatic groups, they can build even larger molecules. And so this allows you to really systematically tune the structural parameters of the system, changing the side block, building out the core block in order to change the size of the disc, and changing the chemistry you use in order to change some of the interactions between discs, potentially providing you a lot of tunability and customizability in the way you design these molecules and material systems. And so this gives you really a lot of flexibility with chemistry in terms of designing self-assembly molecules. And I think this is one of the big advantages of supramolecular chemistry in terms of a way to prepare gels, is being able to build these types of small molecules that then self-assemble into large structures. So being able to use small molecule chemistry to build very well-defined molecules that then spontaneously self-assemble into final materials. And so this offers a really nice approach into the preparation of hydrogel-based materials. And so what you'll see is on the next slide, we'll look at a few materials in particular and compare some of the effects of structure. So one of the molecules that's going to be of interest is molecule 2D. So molecule 2D has this medium-sized urea core, and then it has this branched alkyl side chain. We'll also look at molecule 2F, which has the large core and the branched alkyl side chain. And then we'll look at molecule 1D, which has the medium amide core and the branched alkyl side chain. So we can compare all of these different molecules by neutron scattering and also visualize what's happening in the materials by atomic force microscopy. And so in this case, some of the materials simply coated onto a surface by atomic force microscopy. What you see is that in 1D, you form these large patchy types of structures from the amide-based self-assembling material, whereas 2D and 2F tend to form more fibrillar-like structures. The neutron scattering, again, here shows its real advantage because it allows you to characterize the structure of these fibrils in situ. So rather than having to do sample preparation that's required for AFM imaging, you can really just characterize them in their native environment and get direct information about the self-assembly. And what the authors see is that across a wide range of Q, at intermediate Qs, essentially a plot of I versus Q on a log-log axis shows a slope of -1, indicative of I scaling as Q to the -1 behavior, which is consistent with rod-like objects. And then when they go to low enough, or high enough Q, you start to see these structure factor, form factor peaks, indicative of the size of the radius of the cylinder. And so from this structure, they can determine that these materials are of cylindrical shape, and they're relatively long, resulting in this rod-like Q to the -1 scaling, so with a length that's much, much larger than the radius R. Basically inferring this sort of fibrillar shape that they also have seen in the AFM. What you see in the upper SANS curve is that both sample 2D and sample 2F show qualitatively similar structures. Some difference in the particular size of the molecules. In particular, you see that in 2F, the peaks are shifted to a little bit lower Q, indicative of a slightly larger radius, and this is consistent with the fact that the F core, the urea core 2F, is a large core, whereas the urea core 2D is a medium core, and so you'd expect to see some increase in the characteristic diameter or radius of the fibril. What you then see in the bottom is that a comparison between 2D and 1D shows significantly different structures. In 1D, you never see this characteristic region of rod-like scaling. Essentially, you're not forming self-assembled fibrils, and you don't see the characteristic fibrillar structure coming out of the SANS. So what's seen in the SANS, the sort of in situ characterization, corresponds very nicely with the observed structures in the atomic force microscopy imaging. All right. Another example of self-assembly that I'd like to discuss is self-assembly of worm-like micelles. And this is a fantastic example of surfactant self-assembly as it starts to interface and make materials that can have many properties similar to hydrogels and other types of soft materials. So surfactants will self-assemble into different shapes of micelles, spherical micelles, worm-like micelles, or vesicles based on the molecular packing parameter, essentially concept of molecular shape, the size of the head group versus the size of the tail group of the surfactant. This concept has been developed and discussed extensively by folks like Israel-Tuvili, who has a very nice discussion of these packing parameter effects in his book. So for appropriate choice of surfactants, you can form worm-like micelles, essentially intermediate values of the packing parameter between what's necessary to form spherical micelles and vesicles. And these worm-like micelles will have a circular cross-section with a radius RCS And then they'll be very, very long in general. So some can even be many microns in length. And they have some flexibility in them. So you can imagine this worm-like micelle as being a string, and the string has some short length scale rigidity, given essentially by a persistence length, which is labeled as L sub p, which is a function of the material you use to design the worm-like micelle. And so you can imagine this, in some sense, as being like a very, very long polymer chain or long molecular thread, where now this polymer is self-assembled actually from a large aggregate of different surfactant structures. So if you imagine these worm-like micelles then as being like a polymer molecule with some persistence length and some diameter, then if you take these molecules or take these self-assembled structures and reach a certain concentration, you can imagine these worm-like micelles might start to entangle and actually wrap around one another, and so then they could form something with properties similar to an entangled polymer solution. And you may also imagine that you could potentially even get defects in the self-assembly that could lead to different sorts of physical junctions between the structures. But what's shown here in this schematic is really the formation of different topological entanglements between worm-like micelles that can lead to mechanical properties in these micellar solutions that resemble entangled polymer solutions or associating polymer gels. And so when we look at the linear oscillatory shear rheology shown on the lower right-hand side of this system, you see that at high frequencies we see an elastic modulus much greater than the viscous modulus, characteristic of solid-like behavior. With decreasing frequency we see a crossover and then followed by a liquid-like regime at lower frequency. And this is qualitatively similar to what you see from an entangled polymer solution, but now it's formed from small molecule surfactants. So in addition, so the phase behavior of these worm-like micelles for the particular example system that I'd like to discuss, which is a really nice example because it does some very interesting analysis in terms of mechanical deformation of simultaneous stands and rheology to study mechanical deformation in these materials. So in this particular system, what you see is that the worm-like micelle assembly is induced by adding salt to a cationic surfactant. So the salt is sodium salicylate, and the cationic surfactant is EHAC, which has an ammonium head group. And so the addition of the salt actually leads to a dramatic increase in the viscosity. This is characteristic of the self-assembly and formation of these entangled micellar solutions. It eventually passes through a two-phase region at high enough salt concentration, and then at high salt you see another peak due to the formation of these sort of entangled networks. And there's a cryo TEM image, which is a little bit small, but hopefully shows you the same idea that you can get these sort of entangled micellar structures. And in the cryo-EM, this looks very, very similar to fibrillar networks of gel-forming molecules, the type of things that we were just discussing. So when the authors use neutron scattering to characterize the structure under quiescent conditions, what they're able to obtain a relatively good fit with the cylindrical form factor. And so the raw data is shown here by the triangular symbols, and the cylindrical form factor is the solid line here, illustrating the self-assembly of these materials. And so this is consistent with what they observed by cryo-TEM and with what we think we would have in a worm-like micellar system, where essentially the worm-like micelle is a long cylinder of some characteristic persistence length. And so at length scales less than that persistence length, you will essentially have a cylindrical shape to the worm-like micelle. And it's at these length scales that they're getting a very good fit to this cylinder form factor, and that's consistent. So again, the observation from microscopy and sands really give us a consistent picture of the structure of these materials. Now, one of the fantastic advantages of neutron scattering in this type of system is the ability to do mechanical measurements and neutron scattering simultaneously, and therefore to be able to look at the structure of the system under deformation in a neutron scattering beamline. And so these authors use a Taylor-Couette cell in order to do this measurement. So a Taylor-Couette cell works by essentially having an outer cylindrical cup, and inside that outer cup sits an inner bob, and these two rotate relative to one another they can either both rotate or one or the other rotates. In this work, I believe they predominantly rotate the inner cylinder, and the fluid exists in a gap between the two cylinders. And so what you have is a narrow cylindrical gap between the two cylinders in which the fluid moves, and this allows you to produce relatively sensitive measurements of fluids, even with a reasonably low viscosity. So it's a very sensitive way to make measurements of the fluids. And it's fantastic in terms of SANS measurement, because by changing the orientation of the Taylor-Couette cell relative to the orientation of the neutron scattering beam, you can probe structure in different directions within the material. So they probed in 3 different directions. So first, they probe a 1-2 direction, which is essentially going down the rotation axis of the Taylor-Couette cell. The second thing they do is probe in a 2-3 direction, which is shooting through the center of the cell, right? And so then the scattering you're looking at, because your beam is incident on the material, right as the flow is perpendicular to the beam, this is a 2-3 direction. And then when you're looking at then they can move the beam across to the side of the cell, such that the flow is going directly into or away from the direction of the beam. And this gives you the 1-3 scattering direction. So this Taylor-Couette cell is very nice for the ability to reposition the beam in a lot of different directions in order to hone in on the type of scattering direction you want and really look at the change in structure of the material in all 3 dimensions during rheological deformation. So on the next slide, we show the effects of alignment and shear, basically SANS patterns in many different planes. The scattering in the 1-3 plane, the 2-3 plane, and the 1-2 plane. Moving down the images, we have different characteristic shear rates, 1 inverse second all the way up to 80 inverse seconds. And then these small numbers over the 1-2 planes are the different characteristic gap sizes of the Taylor-Couette cell. What you see is that in the 1-3 plane and in the 1-2 plane in particular, the application of shear leads to a highly anisotropic structure within the gel. Right, so at relatively low shear rates, we see that the structure stays largely isotropic, and this is consistent with the fact that when you shear the material on a time scale slower than its characteristic time scale for relaxation, then the material is always relaxing back to its isotropic structure faster than you're able to deform it. But when you increase the rate of deformation, then you can create significant alignment in the structure, and we see that in the 1-3 planes and in the 1-2 planes. And so essentially we see the appearance of these structures known as butterfly patterns in the deformed material, and these butterfly patterns are consistent with the formation of aligned structures in the cylindrical micellar material. And you see that the direction is different based on the flow direction relative to the SANS curve. So the authors then analyzed their data by calculating an alignment factor, which is what I've written here as A sub f of q. And the alignment factor is essentially an angular average over the X-ray scattering data. Colorado School of Mines has, let me interrupt for a minute. Colorado School of Mines has asked a question. In these structures, if we want to get relaxation spectra, do we need inverse of frequency only? That's a great question. So I think what type of relaxation spectra you're looking at, I should preface this with this. I think this question depends on what type of relaxation spectra you're looking at. There's one aspect of that which would be inelastic neutron scattering measurements to access certain types of relaxation, essentially with dynamic structure factors. And then there's the idea of looking at relaxation spectra from mechanical data. And so let me answer the mechanical data question, because I think this is probably more relevant to the relatively long time scales that we're thinking about in terms of the relaxation times in these processes. So getting a relaxation spectrum out of mechanical data isn't just as simple as inverting the frequency. Because the relaxations with many different time constants are overlapping. Essentially, what one has to do is a similar process to extracting size distributions out of DLS or other things where you extract a spectrum of different relaxation times. So generally what's done is you have some sort of a relaxation spectrum that you propose in a model. So you develop a relaxation model for a structure, and you try to fit that model to the mechanical data and assess the quality of the fit as a method for understanding whether your model is capturing the right relaxation spectrum. So for example, if you hypothesized that you had a reptative relaxation spectrum or a Rouse relaxation spectrum, you could fit this to the mechanical data that you produce and then use that in order to understand whether you have the right relaxation spectrum and potentially to measure a small number of fundamental parameters about your material. But simply saying that each inverse frequency gives a characteristic contribution to the relaxation spectrum, it's not quite so simple, because the relaxations at every different characteristic timescale all become mixed together in the real material. And so this requires basically a fitting type of approach rather than simply a direct computation from the raw data type of approach in order to extract that spectrum. Hopefully that does a reasonable job of answering the question you were meaning to ask. So the quantitative analysis of alignment performed by the authors essentially performed an angular average of the scattering intensity, so I of Q and phi, and they use cosine of 2 phi minus beta. So beta is essentially the tilt angle off of whatever they define as the zero angle of their axis, so the angle of alignment relative to the flow axis. And you use 2 phi here because the material should be symmetric with respect to 180 degree rotation. Right? Essentially the worm-like micelle has no head or tail. It's an aligned object, but since both of the ends should be the same, then the molecule is symmetric with respect to a 180 degree flip in the flow field. And so this is why I use the 2 phi. So they do this integration. This allows them to construct an alignment factor, which is directly analogous to a liquid crystalline order parameter. And what they see is that in these aligning planes, as you increase the shear rate, you get a dramatic drop in the alignment factor. So you essentially see this drop in the alignment factor in this case is consistent with alignment of the worm-like micelles parallel to the flow field, I believe. So again here, sands during deformation is now allowing you to understand things about structural alignment during flow, which would be very difficult to access in other types of techniques. So another type of gel that's very, very interesting to look at during deformation is a nanocomposite gel. Nanocomposite gels have attracted a great deal of interest over the last 10 years in particular, due to this desire to be able to engineer gels of high extensibility and high toughness. Gels that match, for example, the properties of skin or of muscle tissue. Right? When you imagine these types of tissues, compare them to what you think of as jello or jelly in food. Right? Jello and jelly are very brittle. They crack and fracture easily with very little energy. We'd like to make gels like skin or tissue that can stretch, so you can pull on and have some extensibility, and that are highly tough and durable. And so nanocomposite gels have had a great deal of success in achieving these types of properties. So I show a couple of examples. So one is an extension ratio of nanocomposite gel developed by Shibayama's group. So the extension ratio, again, down here is lambda, and this is a function of stress in kilopascals. And so they show as a comparison two different gels that illustrates just how amazing nanocomposite gels are. NC4 is a nanocomposite gel, and OR3 is a traditional chemically cross-linked gel, I believe cross-linked with bisacrylamide. And so these nanocomposite gels in this figure, will show some schematic illustrations in a bit. The nanocomposite gel is essentially composed of a clay platelet surrounded by polymer. So actually, let me skip ahead and have a look at an example figure. So up here in case A, essentially these gels are clay platelets with polymer grafted or attached to the surface, and the polymer links together the different clay platelets, and thus the name nanocomposite gel. You have clay or silicate, discs of clay or silicate linked with and surrounded by polymers in order to produce this nanocomposite type of structure. And so essentially the clay acts as the cross-linking agent in the gel, rather than adding a chemical cross-linking agent that links together the different polymer strands. So in the chemically cross-linked gel, you see the material is stretched, and it actually fails at a stretch ratio below 2, something just above 1, and at a stress of only about 10 kilopascals. But the nanocomposite gel can be extended to very high stresses, greater than 80 kilopascals, and a stretch ratio greater than 10. Right, so imagine this in your own kitchen, trying to stretch a block of Jell-O gelatin to a stretch ratio greater than 10. Right, if you try to stretch Jell-O gelatin, you get a property similar to this OR3 chemically cross-linked gel. So this ability to go to these long stretch ratios, this is much more like a rubber band than it is like what we traditionally envision a hydrogel. And so this is a really fantastic and fascinating mechanical property in these gels, and it leads us to think very hard about what has happened in the structure of these gels that has led to these dramatically different properties, so that we can develop general engineering and design rules for building such systems. One of the other things to note is about these materials mechanically before we start to look at their structures in the right-hand figure. And so in this we analyze the volume of the gel. So the plot here shows essentially the NC4 versus the calculated value. So T over T naught is the thickness of the gel relative to initial thickness as it's being extended. And so the calculated assumes a volume conserving material. And so what's shown is that the NC4 it decreases slightly faster, so appears to go down slightly in volume, but approximately conserves volume during the deformation. And this is traditional for polymer network type of materials, although for hydrogels in particular, because you can have solvent transfer in and out of the material, essentially poroelastic effects during deformation, volume conservation is not necessarily held in all hydrogel materials. So the sand structure of these materials, in this case we have a clear multi-phase material, as we have in many of the gel structures. There's a solvent present with its characteristic scattering length density. There's a clay platelet present with its characteristic scattering length density. And there is a polymer present with its characteristic scattering length density. And so we refer to these as polymer is subscript P, solvent is subscript S, and clay is subscript C in the attached equations. And so the scattering from the system, if you assume that the system, if you assume that on mixing the volume is conserved, can be modeled as the volume fraction of polymer times the volume fraction of solvent with a polymer-solvent contrast factor, and then the polymer-polymer structure factor, plus a term for the clay-solvent volume fractions, the clay-solvent scattering, and the clay-clay structure, and then plus 2 times polymer-clay with different scattering contrasts, and then a polymer-clay cross-interaction. And so the first experiment that I want to show is looking just at what is the structure of clay in these types of solutions. And so this data shown here on the right is SANS data just for clay as a function of the composition between water and D2O in the material. So essentially a contrast matching experiment as the solvent composition is altered in order to be able to contrast match out the clay. And what's seen is that in all cases the clay can be fit essentially by a form factor. So the SCC includes all of the structure factor and form factor contribution. In this case, in the solution, it's just the form factor contribution. And so this is a form factor for a disc-like molecule averaged over angular orientation. And you see a relatively good fit to these disc-shaped form factors in the solid black lines. And you see the intensity modulates up or down with changing D2O to H2O ratio, essentially due to contrast matching, illustrating that the clay scattering can be contrast matched out by tuning the D2O and the water. And this is really where one of the areas where SANS is particularly powerful in the characterization of these soft materials is the ability to use contrast matching to isolate structural contributions from only one of the different components within the system. So now the authors did tensile deformation of the materials in two different scattering conditions. One is pure D2O, so no attempt to contrast match out the clay or the polymer, and another one is contrast matching out the clay. And so looking at these figures, what you see is 8 different scattering panels as a function of 2 variables. So the first is the no contrast match case. And in this case, we have lambda equals 1, 2, 4, and 6. So essentially, we're seeing the undeformed case, lambda equals 1, on the far left-hand side, and increasingly large deformations as we move towards the right across the structure. We see 2 different SANS patterns, one taken at 2 meters, capturing relatively higher Q structures, and one taken at 8 meters, capturing relatively lower Q structures in the material. And what the authors see is that, particularly in the lower Q sands, as you start to deform the material, they see the formation of an anomalous butterfly pattern at higher deformations, indicative of the formation of some sort of anisotropic or aligned structure in the material as it starts to become highly deformed. But from this type of measurement, it's hard to say how the clay is contributing and how the polymer is contributing to this overall pattern. So what the authors did next was to repeat the same experiment with a contrast match between clay and water, such that they isolate specifically the structure in the material originating from the polymer aspect of the nano composite gel. And again, what they see is particularly, so again, we have the same 4 stretch ratios and the same 2 sample detector distances, and particularly in the low Q material, the high sample detector distance, 8 meters, they see the appearance of this butterfly pattern, which indicates anisotropy, with the 2 lobes forming in the stretching direction along the sands pattern. And so based on the appearance of these appearance and quantitative analysis of this anisotropy, the authors infer from this a structural hypothesis about what's happening during deformation. And so I show here case A, which is a no contrast matching case, and then case B, the contrast matching case. And so in these cartoons, you see they look different. It's not meaning to imply that the gels are different, but rather that the platelets in case B are just shown in these very light dashed lines because they've been contrast matched out. So the idea of the figure here is to communicate that you can no longer see the platelets in case B, but you can see them in case A because of the way the contrast has been designed into the system. And so in case A, what the authors the structural hypothesis is that as the material is pulled, the clay platelets, which are contributing significantly to the scattering, are now aligning with their normals parallel to the direction of extension. Essentially, so that the polymer chains, which are predominantly linked to their large flat faces, can form aligned connections between the large flat faces of the different clay molecules. So as the gel is stretched, the polymers become more and more aligned, and the aligning of these polymers pulls the clay platelets such that their normals are aligned parallel to the direction of extension. And so in case A, you see the mix of clay alignment and polymer alignment, whereas in case B, you still see this alignment, and this is only due now to the polymer because the clay has been contrast matched out of the system. And so case B also suggests that you have strong alignment in the polymer material. All right, so the tensile data from sands can be quantified using Ornstein-Zernike plots again, and so here they analyze both in the parallel direction and can extract a parallel correlation length, essentially from the parallel scattering intensity, and in the perpendicular direction, where you can extract a perpendicular scattering length. So the plots are shown here for parallel and perpendicular on the right-hand side, plotted intensity as a function of Q, and then fit. They perform the fit to the Ornstein-Zernike function and extract the correlation length. What you see is that in the parallel direction, the correlation length is significantly larger than in the perpendicular direction. They start out in the undeformed state as being equal, down around 80 nanometers, whereas deformation causes the parallel correlation length to grow and the perpendicular correlation length to remain relatively unchanged within the error bar of the material. And this growing in the parallel correlation length is indicative of this alignment and structuring of the materials as the clay particles become aligned and become spaced based on the linking length of the polymer chains between the different clay particles. All right, so one final topic that I'd like to discuss comes from a second study that was followed on this detailed sands and tensiometry study a few years later by the same group, which illustrates an interesting piece of sands analysis that can be applied to understanding soft materials. And this is the idea of using all three of the different partial structure factors that potentially appear in this multi-component system in order to try to infer the relative ordering and interaction between different components in the system. And to be able to do this in an in situ sense without taking the system out of its native gel environment. So the theoretical basis for the analysis is shown on this slide. And so the specific question that we pose is, when the clay particles are incorporated into the gel, is there a dense polymer layer surrounding the clay particles, or is there no such polymer layer? And so if there is a polymer layer, then the structure factors, so if there is a polymer layer, you can imagine you have water with a polymer layer, and then water on the outside with the polymer layer, and then a clay particle on the inside. Or you can imagine a scenario where you have just the water and then a clay particle on the inside with no dense polymer layer surrounding it. And so in all three of these different cases, you can calculate structure factors: polymer-polymer structure factor, clay-clay structure factor, and a clay-polymer structure factor, S of Cp. Right? The specific parameters that are used in the calculations are shown down here in the inset on the graph. And what's very interesting to note is that in particular, so the clay structure factor remains roughly the same because the clay disk is a rigid object in both cases. You'll notice that the quantitative axis on this scale for S, the y-axis scale, changes significantly from about 4 to about 14 times 10 to the minus 21. And so even though the SCC is a lot lower, looks a lot lower on the top graph, you'll notice that quantitatively the values are about the same. This is what you'd expect because the clay particle is a rigid object of a certain size. You see some change in the polymer-polymer structure factor, as it potentially you'd see a much different structure if it's in a layer. But what's particularly notable is that you see a strong effect in the cross interaction. In particular, if you have the polymer aggregating or assembling near the surface of the clay particle, then you expect to have a positive value for this cross structure factor for a relatively significant part of the Q range, indicating that there's some sort of attractive interaction or correlation between the polymer and the clay. If you don't have any polymer near the surface of the clay, then you expect to have a slightly negative value of this structure factor, essentially indicating that there's an anti-correlation. So where the particle is, there tends not to be polymer in that area, and so a small negative value of this cross correlation contribution. So the authors can then perform the experiment and try to measure the different partial structure factors. And the way they do this is by essentially running the SANS experiment at varying levels of D2O in a D2O-H2O blend, so that you vary each of the three different contrast factors in this equation all simultaneously. And by varying each of these three contrast factors in a way that you can vary the weighting of each of these three different structure factors in the overall sum for the intensity. And so then essentially you can back out the values of all these from a fit to the experimental data. And when they do this, what you see is that as predicted, you have the clay-clay structure factor, which looks relatively similar to the predicted value quantitatively, a polymer-polymer structure factor, and then the clay-polymer structure factor, which actually has a positive value, intermediate between the polymer-polymer and clay-clay factors. And so this positive value is what's predicted if there's some sort of an interaction causing the polymer to form a layer on the outside of the clay particle. And so this really elegant SANS analysis gives the researchers a way to understand that there are in fact polymer layers forming densely on the outside of the clay particles, in addition to the sort of loose network connectivity linking the clay particles together. And so this is a really neat way to gain structural information and interaction information about the system, which is uniquely enabled by a sands contrast matching type of experiment. Alright, so now I'd like to summarize. So said a whole lot of different things about gel structure characterization. I think when you look at the many different types of gels and the variety of gels, I think what you see is that there's no one specific structure or one specific type of molecular design that leads to gelation. But going back to the beginning, the definition given by Richard Jones, that many different types of things can form a network in a material. And when you form a network that's capable of bearing mechanical stress, then you have many different ways to form this gel. And so you can do it by linking together flexible polymer chains, something you envision like a net. You can do it by linking together rigid self-assembled fibrils, by self-assembling block copolymers, by building structures such as nanocomposites or jammed colloidal structures, all of which can potentially bear and transmit load through a network. And these networks can be formed covalently or non-covalently. One of the challenges in understanding these network structures is understanding how all the different structures that can be used to build networks then have structure property relationships that translate into the final mechanics of the network. And this is a really grand challenge because we'd like to be able to engineer networks with properties such as toughness or extensibility, as we saw in some of these double network gels and nanocomposite gels. And being able to do this engineering really requires us to get a fundamental understanding of the structure property relationships in these systems. And this is where sands can potentially offer us a great deal of opportunity to do this work, because sands gives us the ability to probe gel structure in situ, to see these nanoscale building blocks that are used to assemble the network, and to look at the nanoscale properties of the gel. So to understand the structure and assembly of fibrils, or to understand the connectivity of a polymer network within the gel, and then to understand aspects of material construction such as its pore size and its nano or macro scale inhomogeneity that will fundamentally affect transport, and again also fundamentally affect mechanics. Since when we consider mechanics, we often consider a gel as a homogeneous material, but if it has structural inhomogeneity, this structural inhomogeneity can lead us to reconsider the type of mechanical model that we believe is appropriate for the gel. So sands really provides you a powerful in situ structural probe. In addition, sands can be combined with things like rheology or tensiometry. We saw a few great examples of that today, really one of each, that allows you to study structural evolution and deformation in situ. And while there are many applications in technology for gels, a large variety of them still have to do with the fact that what we really like to do is have solid-like properties in something that's predominantly solvent. And so understanding these solid-like properties, understanding structure and how it impacts transport, which is relevant in terms of the solvent and the liquid-like behavior of the system, is really very fundamentally interesting in terms of the science of these hydrogels. So hopefully this provides a basic starting point for thinking about some of these questions and some of the science of gels, and I'd be very happy to take any questions. I see Ming has asked another question. How small of a wave vector can we get nowadays? I'm interested in this because I think smaller Q helps us study larger length scale, like the colloidal aggregates on the micrometer scale. So it's another great question, Ming. So I think in all the studies I highlighted, I believe that Helgeson's study, which was done at NIST, goes to some of the lowest Q that they can access. So you can see here they're getting Qs below 10 to the minus 4 inverse angstroms off of a USANS instrument. Unfortunately, I think there are probably many more people participating in the class who are more experts than I am about the individual performance of all the different instruments around the country that can access this USANS range. So I would hold this up as one example of going to very low Q, but I would say consulting with all the relevant instrument experts about what their specific instrument can do under what conditions would probably be appropriate in order to see what's the absolute smallest Q that you can go to. Another thing to consider is that many of the same in situ advantages of neutron scattering are offered by light scattering when you start to push to extremely low Q. And so there have been a significant number of studies that I didn't talk about looking at things like dynamic light scattering and static light scattering analysis of structures in hydrogels that I think is a little bit beyond the scope of what's been discussed in this course. But light scattering methods should be considered for pushing to extremely low Q and trying to analyze self-assembly in gels. Thanks very much.